afternoon or evening, if it may be, to spend a little time with us. I hope the information is useful and helpful, and we're going to be concise and then have a nice open Q&A session at the end of the web event. So let's get started. I've introduced Jim and Paul. I want to say real quickly a few things about the webinar platform. This is a recorded event, and we'll send a link out to you. So if there's any slides or important information you miss, you will get that information in the link. Participants will be muted. What is that background noise? Participants will be muted until the Q&A session. The chat box is open and live, and you're welcome to drop questions in along the way. We'll try to answer them if we can, or we'll answer them later in the Q&A or privately. None of this is private. You're welcome to send this presentation to anybody you like. And if you have sensitive questions or sensitive issues, we would say reserve those for follow-up email to the web event. I'm sure everybody's pretty familiar with Berkeley Nucleonics, but we did start here in Berkeley at the Lawrence Radiation Lab in 1963. We began our journey down nuclear electronics with NIM modules and power supplies, and have expanded into other areas of science and industry as well. We now have a full RF and microwave division, and also a chemistry and high energy physics based test and measurement department. Actually, the photo behind me, that's one of our test labs. That's not a live shot, I must admit. Otherwise, those guys would seem very still, not working too hard. But they're working on analog design, so we do a lot of front end high speed analog as well. But we're here to talk about nuclear. We do have reps around the country as well who can give you local support. These are reps that carry our product lines and support customers who need some hand-holding, training. We do a lot of on-site help as well. Internationally, we're also well represented. We've got a variety of different organizations who can help you with currency, language, translation, on-site service, all that kind of stuff. This short lunch and learn, we want to keep it short. It's just a lunch period event. We'll talk a little bit about the history of cerium and lanthanum, a little bit about the applications, talk about technical attributes. We've got a show and tell video, and then that Q&A session, like I said. Okay, now here is a little history of scintillation detectors. I will try one more time on Paul and see if we can get him in on this. Obviously, the real bulk of the development occurred after the invention of the photomultiplier tube. And you can see all the way up at 2000, in the early 2000s is when lanthanum bromide was discovered. And then the cerium bromide followed lanthanum bromide as well. Jim, do you have any additional comments on the history of the scintillation detectors?
No, not really. Paul can fill us in on that, I think, a little bit better.
Okay. We'll keep working on getting Paul into the event here. Okay. And so good. So Jim, I'm going to let you jump in here and give us sort of that top level look at comparing these two scintillators.
All right. Good morning, everybody. We want to focus on cerium bromide and lanthanum bromide and how they compare. They're both very good detectors, but we want to talk about some of the characteristics of these. First of all, on cerium bromide, we have some outstanding characteristics, short decay time, very high yield, 60,000 photons per MeV. But the energy resolution and the background are what I really want to home in on. These detectors are available in 2x2 inch, 3x3, 3x6. Paul is going to tell you a little bit more about that at the end of the presentation. But very large detectors are available, and I would just want you to know that. Now we're going to go talk, next slide, David.
Okay. Yeah.
A lot of applications for lanthanum bromide and a lot of applications for cerium bromide. BNC deals with these types of customers that come in with all different kinds of applications. And I just want to give you a list here that is specifically very good for cerium bromide. A lot of these are good for lanthanum bromide as well. So let's go to the next slide. So I want to tell you a little bit about the performance, especially in terms of resolution and background. Lanthanum bromide is quoted at 3%, and the cerium bromide is 4% resolution. Now, these are all specified at cesium 137, the 662 keV line, full width at half maximum. All the scintillators are specified at that energy. Not necessarily is that the resolution that's going to stay at low and high background or low and high energies, but that's the resolution specifically at that moderately high energy of cesium 137. Actually, sodium iodide does fairly well at 7%, and it's used extensively for high energies. But we're wanting to talk today about how well we can separate some of these very closely spaced lines. And we're going to do that. And I'm going to show you a picture of how well the bismuth 609 keV energy separates the cesium line at 662. We'll do that on the first slide that we're going to show. The most important thing is how well does it do in lower energies, and how well do these detectors perform as far as background is concerned. And to do this, we're going to show a weapons grade plutonium spectrum, and we're going to talk about that and the low energy and high energy background. Next slide.
Right. Okay.
So here's what I wanted to show you in cerium bromide. Both lanthanum bromide and cerium bromide can separate these two peaks. This is a spectrum that's often shown for the ability to separate the bismuth 214, which is a daughter in the radium spectrum. And you see the marker right on the 609, and you see cesium peak just above that. So those two are just right together, and the separation is very nice. If you look at this with sodium iodide, you would be seeing primarily one peak on top of the other. Maybe just a little bit of the ability to see one, especially if the cesium were very large in comparison to the 609 bismuth, then yes, you might be able to see it, but I doubt if you'll be able to identify both of these lines. And so the identification is important when you do good separation. The next view graph.
Okay. Yeah. So you've got control of the arrow. Okay.
Okay. Now the next view graph is showing us what we expect of background, and it is specifically in both cases cerium bromide and lanthanum bromide from the actinium-227 complex. This is in the uranium chain, and that background is very low for cerium bromide. And for the standard detector, we see that background primarily in the 1300 to 2200 keV region, and the standard crystal will exhibit 0.025 counts per second per cubic centimeter of material. And then there is also, and this is fairly new now, fairly low, ultra low background, which is at 0.001 counts per second per cubic centimeter. And I might mention that that's only by selection, not by chemistry, but selection of these crystals. Both of these standard and ultra low background crystals are readily available.
Jim, when you talk about selection, are you referring to a crystal grower is growing a dozen crystals and there's just a natural physics involved that have some with lower background than others? Is that what you mean by selection?
Yes, there's various sources of this material coming from different areas, but if these sources are show lower backgrounds, then we will select that. And in a moment, we'll see a picture of this, and the picture is worth 1,000 words. And we'll show that picture in just a moment. But I want to contrast this low background and the standard background with lanthanum bromide. So when we look at lanthanum bromide, we have all this actinium, but we also have intrinsic background from radioactive lanthanum-138. This isotope is actually in the crystal, and so we have a couple of different decay chains from the lanthanum-138, and it can give you contributions of 100 times that of cerium bromide, depending upon what part of the spectrum you're in, and even larger than 100 times. So we're going to show that slide right now.
Okay. Coming right up.
So here we have a picture of lanthanum bromide at the top trace in black. We have the red dotted and solid lines, which are the cerium bromide. And then just for your information, we also have sodium iodide shown in blue. The vertical scale, you notice that the vertical scale here is in log. That vertical scale is in log. And so when we look at some of these traces, the lanthanum bromide at the top and the cerium bromide in red, we see easily a factor of 100 in places, a little bit lower in other places, but even higher than 100 difference in the area where K40, potassium 40, is in the 1400s. So that's right about here. And then down in the 700 keV area up into the 800, we have another decay of lanthanum-138. We have a lot of gamma radiation in that area. And then we have a lot of radiation down here at very low energies. And in fact, if you just look at a background of lanthanum by itself without any sources, you'd see a huge peak like the X-ray peak of cesium-137. So you have that area, and I want to point to this area right in here. That area right in there, do you see where that starts to go up exponentially in the 100 to 200 keV area?
Yeah, you're talking about the little red and black.
I'm talking about this black area in here that just goes up exponentially, right up to the maximum, which can be as high as 100 and 120, 140 counts per second per cubic centimeter. Now, it's very important for me to tell you that these spectrum oftentimes are shown for different sizes of detectors, and that's not fair. This is shown for each detector being the same size, namely 2 by 2 inches. So we have 2 inches in diameter, 2 inches thickness, and each one of these, sodium iodide, cerium bromide, lanthanum bromide, are all the same size detector. Okay. Now, with this, we're going to move into the next slide, which is actually a picture of weapons grade plutonium.
Should I jump in there?
Yes.
Yeah, okay. Good.
So on the right, we have lanthanum bromide, and lanthanum bromide does quite well. It has a very good resolution. On the left, we have cerium bromide. And I first want to draw your attention to this area right in here where this cursor is a little bit tricky, but right here, right above that arrow, you'll see the 3 little peaks of plutonium-239. So that's 332, 375, and 414 keV. Those 3 little peaks are a triplet, and you see very clearly that we have good enough resolution to pull those 3 little peaks out. If we were to look at that with sodium iodide, we would see 1 peak in there. A little bit sloppy peak, but still you cannot ascertain these 3 little energies unless you get something like lanthanum or cerium bromide. Looking at that area with the lanthanum bromide, we see the 3 little peaks there. And I'll have to apologize at this point. The background is a little bit higher right here because the vertical is a little bit different scale than you see on the cerium bromide. I apologize for that because we are at the mercy of whatever the government sends us in the way of plutonium and uranium, especially high enrichment sources. We're glad to get them, but we can't control it. In other words, we do not carry around plutonium, and I'm thankful for that because I worked with it at Lawrence Livermore Lab for many years, and I'm glad to be away from it. But we do have a very good picture of here, and since the energy scales are very close to each other, then we can talk about the resolution. These 3 lines are very well separated in both cases. I think most of you will probably recognize that as we drop in energy, none of these detectors hold the same resolution in percentage. And so we do see both of these resolutions decrease in energy. Now let's go back down to the americium line. As we go down to the americium line, there's always a lot of americium in plutonium because it grows into the material. So the older the material is, the more plutonium, more americium we have. And so there's no problem in seeing that americium peak unless we've got it heavily shielded. So you see that the width of that line is comparable to the width of the cerium. The cerium might be just a little bit, there it is. The cerium might be just a little bit, the width of that line might be a little bit less. But I've broken out americium by itself so we don't see it on top of the continuum of all this plutonium. So you see americium has a very nice peak down there. The The resolution is something in the order of 13% for the lanthanum. It's in the same ballpark, 13-14%. Most people show it as being the same resolution, but we really don't care whether it's a little bit more or a little bit less. The important thing is to see that triplet in plutonium and be able to see some of these other features, which I'm going to show right now.
Before you do that, Jim, before
yes.
you do that, I love what you're doing. I think Paul's getting his audio worked out.
Oh, good.
I also saw a couple people who said they're on Chrome who can't seem to get the audio. We've got about 80 people on the call. Can people just drop in the chat if the audio is okay and what browser they're using? And that way it might help us real quickly see what browsers people are using, because we want to solve this problem. And audio is good on Safari. Okay. Chrome is good. Using a Chrome on a Mac, no problems. Firefox is okay. I'm not sure, with a couple of people had some iPhone was not okay. Switch to Chrome on a Mac and it's okay. Okay in Firefox, Chrome, fine with Firefox 78 on a Mac. MS Edge is also okay. Blocked on Chrome. Paul, I know Paul. Hi, Paul. I'm sorry. If you want to just call my cell phone, I could put you on speakerphone and you could that might be the best solution at this point. Safari on Mac is okay. iPhone working good now. Safari on Mac. The FDA audio good on Chrome. Okay, thank you so much. That's plenty of feedback. I appreciate that. I'm sorry we stopped the presentation. A couple people seemed unable to connect, and we want to give everybody everything. The good news is we will put this on a video and send it out. So thank you so much, David, for your update as well. Okay, Jim, so we're talking about the triplet and how we can see it there on the left and not on the right.
Well, we can see the triplet on the right. The resolution is extremely good. We have a little bit more background, which we're going to talk about next.
Oh, I'm sorry. I was looking at the americium 241. You're talking about the P239 triplet. Yeah.
But we're looking right now at this americium line, which I have singled out by itself, so it's not sitting on top of all the continuum of plutonium. And you can see that it comes very nicely down to the baseline. It shows a little 26 keV peak just to the left, where I'm pointing to. That little peak is part of the americium spectrum. If we look over at lanthanum bromide up here at the top, we will not see that little peak. And it's doesn't have anything to do with resolution. The resolution here for lanthanum is pretty much as good as the cerium bromide resolution at americium. It's not the resolution, it is the background. And we're going to show that. We've already shown that. And in fact, if you recall, when I talked about that exponential area, which is in the 0 to 200 keV, that area goes up dramatically in the amount of background. So the background isn't proportional all the way through because of these decays of the lanthanum 138. So that just swamps out that little 26 keV line. And there's no sensitivity for ever seeing it because it's a very small peak. Now, is it very important for us to see? Probably not. But nevertheless, there are some areas which are important. And that's what I want to talk about next. If we see the X-ray peak on cesium on cerium bromide, the little X-ray peak, which is right here. I'm having trouble it tends to want to jump. Okay, there we go.
Paul.
And we see.
So I'll just put you on speaker. I'm going to put you on speaker, and then I'll cue you in.
Okay, the X-ray peak, which is written down below, 105 keV. It's a multiplet. This multiplet is made up of about 5 or 6 X-rays. They're from the decay of plutonium to uranium-235. They're hard X-rays. They're K-shell X-rays. And so we see them very nicely over here. And then when we move over here to the lanthanum, we have a hard time seeing it. And that's because of this exponential increase of background in this area. You see just above where I have the pointer, you see just a very small peak. We have not much sensitivity in that area. So it's just gone. Again, we have plenty of americium, more americium than we'd ever want to see when it's unshielded. And so there's no problem seeing the americium. But this small bunch of hard X-rays are just almost gone. This is what the high background does for you in the lanthanum bromide. There's one other little observation that I'd like to draw to your attention, and it has to do with this little peak, which is right here, right above my arrow. I don't want my arrow to cover it, but it's right there. That little peak is a plutonium peak. It's 201 keV. Those of you who are familiar with these kinds of spectrums know that you generally look at that with high purity germanium. It's interesting to me to see this because most scintillators, all scintillators for that matter, we just don't bother looking at the ratios, that is, these very small intensities. And the branching intensity for this particular peak is 0.6. Less than 1 we generally don't look at. But it is very interesting to see this. Is this important for us to see? Not necessarily. I would just want to show it to you because it gives you the feeling that we've got a lot of sensitivity here in cerium bromide. We won't be able to see that in the lanthanum bromide because of the background, but we want to be able to really see these peaks in proportion. We want to be able to see X-rays in proportion, especially as we look at enriched uranium. Highly enriched uranium, those X-rays are important because at a glance we can see whether the material is highly enriched, weapons grade material, or whether it's low enriched, reactor grade material. There are things which people and the physicists want to do in the analysis of these spectrum. So the sensitivity is very important. And if you lose sensitivity for small things or even hard X-rays, you've lost a lot of information in the spectrum. And I can name a lot of other isotopes that we can look at, neptunium, and then other isotopes which are not special nuclear materials. Those are of very big interest to see in low background. And by the way, if you want to get a little insight into special nuclear materials, we have a brand new tutorial on our website, and it's written with a very practical look at special nuclear materials. So you might be interested in doing that. Now let's go back to that previous slide. There we go. And so I just want to reiterate this area, which is right here, where it just exponentially goes up to very high background, we have a very hard time seeing things in perspective, to seeing things proportionally in this area, which is very important. So now I want to mention one more thing about this spectrum. If you look way over here, about 2600 keV, there is a thallium-208, which is very important in looking at this type of material to see whether it's highly enriched or not. In fact, we've had some customers that the first thing they want to look at is this, and then they'll go ahead and interrogate and look further because they have some kind of an application that requires looking at various materials. We don't talk about their applications, but I just want to mention that thallium-208 is a first look at enrichment. And today, masking of these lower energies is done all the time. Shielding and masking with high background. They can wipe out some of these. The little triplet of plutonium is seen usually with a fair amount of shielding, but a lot of the low energies give up the ability to see whether it's enriched or not. And so the thallium-208 is a very important line to look at. But notice how much background we have, a factor of 50 to 70 greater background in lanthanum bromide than we have in the cerium bromide. That sensitivity we don't want to give up. And we don't want to give up because of shielding. That thallium-208 is so active that at that energy, it'll go through lead like butter. I think the mean free path is something like 20 centimeters in lead. So we're not going to really shield that. But what happens is that we do not have good statistics out there. And that's not because of branching intensity. It doesn't have anything to do with branching intensity. We got all kinds of branching intensity to see the thallium-208. What we have is a very poor photo fraction in the detector. And Paul's going to talk about larger detectors, and I think you've seen already that we have 2 by 6 inch detectors. We can get larger detectors, but in a lot of the RIIDs, we have 2 by 2 and 3 by 3 detectors for looking at this. And simply stated, we need to look for 2 or 3 minutes at that point. It's hard for us to train these first line responders to do that, but we've trained them over the years, and when they understand that they need to stay on the acquisition mode for 2 or 3 minutes, and then they'll see something. We do, by the way, I think that a number of you know that we have a very nice way of looking at energies, especially low energies and high energies, in a very convenient mode, and that's called QCC, Quadratic Compression Conversion. And we can speed up the processing of that peak a factor of 8 or 9 times very nicely, and we've proven that. And so that is an advantage when you're wanting to look at very high enrichment material and know that that's what you've gotten. You know, it's enough to have the inverse square law against you. Our first line responders are searching for things, and they may know even where it is, but is it at the top of the barrel? Is it the bottom? Is it the backside? Is it shielded? We get them to move in on it, but because of the inverse square law, you can just lose a lot of your sensitivity. We don't want to lose another 50 to 70 times the sensitivity. So very important for looking at these types of materials and other types of materials. And I've put a sensitivity down here of at least 10 times greater for cerium bromide. It may be 15 times, but I've been very conservative here. You can see that the background is so much more higher, but there are some other factors that have to do with even geometry in looking at the material. With that, I am going to turn it back to David.
Great, thank you, Jim. That's an excellent summary of the issues people face with these two materials. Let me try again to see if I can give Paul an opportunity, having been in this field for so many years, to talk a little bit about the history of scintillator detectors. Can you see the history window there? Paul, can you go? Are you able to?
That slide looks like it's a little too low for me.
Okay.
Is it proper?
Go ahead, Paul.
Can you hear me, David?
Yeah.
So I'm very sorry for all these unexpected audio problems, but a little few words on the history of the high resolution detectors. Around the year 2000, the first developments were made at the Delft University of Technology. Lanthanum bromide was developed there around 2003, and this was the start of a whole new generation of high resolution crystals. And at the moment we have a wide variety of crystals we can choose for our development valve instruments. I have a terrible echo. How is it, Becky?
Yeah, me too. All right. You have to mute your audio, Paul. There you go. Better? Yeah, that's better.
Still better?
Yeah.
Okay. Technology. Okay, at the moment we have a wide variety of high-resolution crystals that you can use for our applications. And cerium bromide followed lanthanum bromide, and the material was developed on a commercial scale actually around 2010. And at the moment we have a wide variety of sizes we can use in designing our instruments. As Jim said, the nice thing about cerium bromide actually is, of course, the background. And can I maybe have slide 24, David?
Yep.
Slide 24.
This guy or 24?
I'm back. Thank you very much. This one, exactly, yeah. So summarizing, actually, cerium bromide has no slow components, which allows us to use the material in very high count rate applications in megahertz spectroscopy. And we know that at high energies, at the multi-MeV energies, the resolution actually is quite comparable to lanthanum bromide. The absence in the background lies in the beta, of course, and in some gamma lines, all originating from lanthanum-138. When we select the material very carefully, the cerium bromide, we also have succeeded in getting rid almost of the actinium background. So we have a very clean spectrum, which you can see here in this graph at the left top of the slide. The crystals are available to 5-inch diameter, 6-inch long these days, and we have a reliable production. Next slide, David. Yeah. We see that cerium bromide actually is an intrinsic scintillator. There is no doping, which is nice from a drawing point of view. It has a very homogeneous response. Decay time is very fast. As I said, no slow components. It's extremely hard for particles and neutrons. And it's a slightly higher emission wavelength than lanthanum bromide. Altogether, we have a very nice material, younger than lanthanum bromide, with very nice properties. And in the future, we are working on co-doping cerium bromide, like was done already with lanthanum bromide, to further improve the resolution to levels between 3 and 3.5% fully Hazmat for cesium-137. We shouldn't forget that there are more nuclides than just cesium-137, and for every application, we have to choose if this is the right material for what we want to measure. And this actually includes some very nice properties of cerium bromide we have available these days.
Yeah. Oh, thank you so much, Paul. That's right. You know, the development never stops at Scionix. We're always so impressed with how you push the technology further and further. So this is exciting for me. Hope you can hear me okay. Let me jump into a couple more quick slides and a quick video. So now we're going to show a quick demonstration of two isotope identifiers, one cerium, one sodium iodide, collecting data of the same source. Here we go.
Today, one of our newest materials, cerium bromide and the SAM isotope identifier. Our peak widths are coming down very quickly. Let me give you an example. This is a sodium iodide and a cerium bromide instrument with both with thorium sources. And if you zoom in on these screens, you see the narrow widths here of the thorium peaks with the cerium as opposed to the widths on the sodium iodide unit. So this very narrow peak width is a result of the 4% resolution cerium bromide system. The SAM cerium, we call it, is available now as a commercial product. You see here the double peak here at about 900 keV as opposed to a single peak on the sodium iodide. And you see also a double peak at about 420 keV as opposed to the sodium iodide, which shows those as a single peak. This peak separation is extremely useful in applications like cesium-134 and 137 deconvolution or plutonium confirmation.
Okay. Wrapping up sorry about the unmute. Yeah, I guess that you may have had that video muted. Were most people able to hear the video? We're experts at technology and detectors. The webinar platform is no audio. Oh boy. All right, let's play one more time. There's a little button at the top left. It says unmute the audio. You may see it up at the top there. So we'll just play
today one of our newest materials, cerium bromide and the SAM isotope identifier. Our peak widths are coming down very quickly. Let me give you an example. This is a sodium iodide and a cerium bromide instrument with both with thorium sources. And if you zoom in on these screens, you see the narrow widths here of the thorium peaks with the cerium as opposed to the widths on the sodium iodide unit. So this very narrow peak width is a result of the 4% resolution cerium bromide system. The SAM cerium, we call it, is available now as a commercial product. You see here the double peak here at about 900 keV as opposed to a single peak on the sodium iodide. And you see also a double peak at about 420 keV as opposed to the sodium iodide, which shows those as a single peak. This peak separation is extremely useful in applications like cesium-134 and 137 deconvolution or plutonium confirmation.
Okay. And if you still didn't get it, we will send this out in a video. Last couple of housekeeping points here. We do have some other webinars on our YouTube channel that are on demand. If you're interested, there's one on choosing your custom detectors, and we look at all the different variables in that process. There's a look at SIPM technology, when it works and when it doesn't make sense, and then some other webinars on test benches and DOE type equipment might be valuable. We have a academy as well that is complimentary. We do short courses on topics like identifying SNM or thermal neutron detectors. The academy is quite easy to get to. You would simply go to Academy. Let me turn on my mouse here. Go simply to Academy, BerkeleyNucleonics.com, and then use this code Berkeley for any of the courses. So they're all complimentary. The one that, for maybe interns or students or people new to nuclear science or the department you're working in, is this Nuclear Radiation 101 course. Just talks about real fundamental, the definition of half-life and the types of radiation and things of that nature. So we think those are useful, especially with so many people stuck at home. And again, they're all complimentary at academy.berkeleynucleonics.com with the registration code Berkeley. And that concludes the webinar for today. And now would be a time where we can try to answer some questions in the chat, or perhaps I can unmute as well, and we can have a sort of a live Q&A. There you go. So now you should be able to ask for permission to unmute your microphone if you'd rather ask for questions like that. It should be a little button there. While we're waiting here, there was a question, Jim, about I don't know if you saw the question, Jim, on the cerium. Thallium 208 has a 583 keV peak in the low energy region for background contribution. What's your comment on experimental observation of lanthanum bromide doped with cerium?
Well, the reason we don't look at the lower energy is the case where, let's just take an example of a shipping container. What the terrorist might do is to shield that very heavily, and you're not going to see a lot of the lower peaks that well, especially if I don't know what the branching intensity is for that lower peak, but the reason we look at that higher peak is because that peak is so active. It will go through lead, the mean free path being 20 centimeters. You're not going to shield it. As I mentioned, those things that we look at, it's more important that we look at that in low background, because the statistics of looking at those things is going to be very poor. So we want the statistics as good as possible. That's the other reason I mentioned QCC. If people have that kind of application where they want to and need to see that peak before they interrogate any further.
Thanks. Richard, is your audio, are you able to hear us okay?
Yes, I can hear you just fine. Can you hear me?
Yeah, you sound great.
Okay, thank you. This may not be a fair question for this particular presentation, but I was wondering if you can comment on the effectiveness of these various crystals at higher energies between, say, 10 and 11 MeV, because that's where I've been trying to work. And I find most literature deals with much lower energies. And I was wondering if you guys had an insight into that kind of thing at all.
Paul, do you want to take that?
Yes, let me first move my audio down again. There we are.
The question was...
Okay. The question was about response.
10 MeV and up.
10 MeV. Well, that's a very good question. The resolution, there's not much known about this, published about this, but the resolution of cerium bromide crystals, 3 inch by 3 inch, at 10 MeV is roughly 105 keV, and the resolution for lanthanum bromide is about 95 keV. It's approximately the same. The interesting thing is at the high energies, the resolutions of cerium bromide and lanthanum bromide are almost comparable. But the nice thing is the cerium bromide is that because it has no slow components, you really can count at extremely high count rates. So the resolutions are of the order of 1% range at 10 MeV.
Mm-hmm. Do you have any comment on the sensitivity in that range?
I didn't understand the question.
Go ahead.
Well, do you have any comment on the sensitivity of these various compounds in that range?
He's asking the sensitivity of the various compounds in that range.
The sensitivity you can calculate via multi-quantum simulation, of course. The density of those materials is 5.3, 5.0. So the sensitivity will definitely be less than, for example, BGO, which has a density of 7 and more Z. But still, it is being used at the moment at those kind of energies in experiments. So it is used, and the fact it makes it attractive is the possibility to run the material at a very high count rate. And of course, resolution is of course great at those energies, the percent range.
I have another question. Richard, let us come back to you because the
Sure.
audio, I think Paul's the expert on this. And if we had, our audio is a little goofy today, but if right after this presentation, if you want to stick around, we'll give you a call directly.
I'd appreciate that.
Other
Thank
questions
you.
in the chat, Paul or Jim. Do either of you want to answer those? The comparison of decay time from lanthanum bromide to cerium bromide, the cost of a small cerium bromide detector.
That's relatively simple. The decay time of the primary decay time of lanthanum bromide and cerium bromide is approximately equivalent. It's about the same. The only thing is that lanthanum bromide has some slow components and cerium bromide does not have those. The decay time is slightly depending on the size of the material. If you're talking about feasible size of crystals, let's say 3 by 3 inch, the decay time is of the order of 20 nanoseconds. That's the main primary component. In cerium bromide, it's the only one.
Got it. How about the cost of the smallest detector for cerium bromide? Maybe 1 cubic centimeter. I mean, yeah.
$few $1,000. The whole thing is not that much.
A few $1,000s. Where can we find data on the radiation hardness of cerium and lanthanum bromide?
There has been publications on radiation damage of cerium bromide that can be found on our website. Has been done in the proton irradiation and also some gamma irradiation studies. Both materials, cerium bromide and lanthanum bromide, but cerium bromide specifically is extremely radiation hard. We're talking about levels of 10,000 gray in megawatt or more. It didn't go higher.
Okay.
So both materials are considered to be radiation hard, yes.
Well, maybe we'll send some links to some of that material in the follow-up email, which, yeah.
Sure.
So we will answer these questions a little more thoroughly in an email. Last question here, the largest dimension that can be produced in cerium bromide?
It's about 5-inch diameter, 6-inch long. At the moment, there's no demand for anything larger, so that's what we do.
Okay, great. Excellent. Anything else? Thank you, Paul. This has been, you've been able to contribute tremendously, even overcoming our technical issues. Thank you to the attendees who've stayed through our ups and downs today and enjoyed the loose but informational Lunch and Learn webinar. Jim, of course, thank you for your contributions as well. Do you have any other closing remarks, Jim or Paul or Richard, now that you're sitting with us?
Don't worry about the audio, Paul. Amsterdam is a long ways away from us.
Yep. Thank you, Jim. Okay. Great. So that concludes the event for today. We will, as I mentioned, put a complete package of information together in an email, which will include a link to this video, but also some of the papers that Paul referenced and some of the maybe more elaborate answers to some of the questions that have been dropped in the chat. The thank yous are piling in, and we appreciate that so much. And I wish you all a enjoyable and safe rest of the week. So thank you again. Bye.
Okay.